In this example, we're told we have a tank that's rolling along a level track, and water is received from a jet that's retained in the tank. So there's water coming out of this jet, has a cross-sectional area A and a velocity V, comes out constant area, constant velocity, and then it's deflected into this tank, this cart. This cart initially has a mass of m naught. Initially, we have some water and the cart together have a total mass m naught. And the tank is to accelerate from rest toward the right with a constant acceleration a. Neglect wind resistance, rolling resistance. Find an algebraic expression for the force as a function of time required to maintain the tank acceleration at constant acceleration. So we're going to apply some force here to make sure that the tank accelerates at a constant rate, or has a constant acceleration. So this will be a linear momentum equation problem because we're trying to find an acceleration of this cart, and you can see that its momentum is changing with time, in part because the velocity is changing, but also because the mass inside the cart is changing as well, so the momentum will change. So let's draw a control volume that surrounds the cart, because that's what we're trying to find the acceleration of. And I'm going to have the control volume just cut across the stream at right angles, right at the inlet there. And the reason I want it cutting across the stream at right angles is it makes the dot product for the mass flow rate term easy, and I just really want to follow the cart as much as possible here. All right, so we're going to apply the linear momentum equation to that. Before I do the linear momentum equation, I'm actually going to do conservation of mass first, and the reason for that is because I know the mass inside the cart is changing with time, and I want to figure out what that is. That'll be useful when we use the linear momentum equation. So we'll write out conservation of mass for that control volume. And then let's first do the time rate of change of mass within the control volume. So that's actually what we're trying to find. So this term is like ddt of the mass inside the control volume. So that's not zero. This is not a steady problem, so we need to keep that in there. And then we can determine the mass flow rate term. The only place where there's mass coming in or out of the control volume is right here at the inlet. So there we'll have the density, and then the relative velocity. Remember that the relative velocity is the velocity of the fluid minus the velocity of the control surface. So the velocity of the fluid will be v in the x direction. Let me put a coordinate system here. I'm going to put the coordinate system, well, you know what, I'll just say headed to the right is a positive x. So the velocity there is v in the I hat direction. Yeah, I guess I should put a coordinate system since I'm talking about it. Let me put it here. And I'll make that capital X and this capital Y. So it's v in the I hat direction is the velocity of the fluid. And then we'll subtract out the velocity of the control surface here. Well, the control surface is moving at a velocity capital U. So the velocity of the control surface will be u in the I hat direction. So that's my relative velocity. Let me highlight what each of these terms corresponds to. So the v I hat is the velocity of the fluid, and the u I hat is the velocity of the control surface. And then the area that it comes in at is going to be the cross-sectional area of the stream A, and it's pointing in the minus x direction because the outward pointing normal vector here is that direction. So it'll be a minus a I hat. So that when we simplify conservation of mass, we're going to have dm dt plus rho, and then we do the dot product. That actually gives me a minus. It'll be a minus rho v minus u a is equal to 0. So time rate of change of mass within the control volume is rho v minus u times a. Okay, so that's how the mass inside the control volume changes with time. We're told that the velocity, so we're given that the velocity of the cart is, well, we know that it's increasing, but we know the acceleration of the tank is a constant a. So that means that the time rate of change of the velocity of the cart is just a constant a, So we can determine the velocity of the cart as a function of time. So we can just solve that differential equation. We can integrate both sides. As t goes from 0 to some final t. The initial velocity of the cart, we're told in the problem statement, is 0. The tank is to accelerate from rest, so it's starting from rest. So the initial velocity is 0, and then we'll go to some final velocity. So u will just be a times t. Remember that the acceleration is a constant, so it can come outside the integral. So that's the velocity. So we can substitute that in. So we have that expression. And then here's another differential equation. So I can go ahead and bring the dt term to the one side and the mass of the control volume to the other side. So it'll look something like that. All I've done is rearrange this so that I keep the dm cv term on the left, bring the dt term to the right-hand side, and we have that, and then I substitute it in for the u. So I can solve this differential equation. Let me integrate both sides. So we have our initial mass to our final mass, and we're told that the initial mass of the cart and water is m naught. And then we have our initial time, 0, and final time, t. So this will be mcv minus m naught is equal to rho times vt minus 1/2 at squared times the area. So that's how the mass in the control volume changes with time. I'll just rewrite it one last time here. So that's just telling us the mass in the cart and how it changes with time. It still isn't giving us the force that we need to keep this at a constant acceleration. So we still have to find that part. So in order to do that part of the problem, we'll apply the linear momentum equation to the same control volume. So let's write that out. Now, actually, when I write this equation out, I'm going to write it in the x direction, but I'm going to use a different coordinate system for this part of the problem. Let me draw this other coordinate system here. It's going to be a little xy coordinate system, and I'll draw a little person here to indicate that that coordinate system is moving with the control volume. So this coordinate system is stuck on top of the control volume here. So it's actually accelerating. I don't have to do it that way. I could still go back and use our fixed coordinate system here, but I find it easier to use this coordinate system for these. It's usually easier to use a coordinate system fixed to the control volume if the control volume is moving. So I'm going to do it from that perspective here. So this is the linear momentum equation in the little x direction. So I'll write out the linear momentum equation for that, and then we'll simplify it. Okay, so there's the linear momentum equation in the x direction using my accelerating coordinate system. And because the coordinate system's accelerating, I have this additional acceleration term in my linear momentum equation. If I used, and by the way, the ax slash x, this is the acceleration of my little coordinate system with respect to the fixed coordinate, big X coordinate system. So it's the acceleration of this coordinate system relative to this fixed one here. Okay. Now, if I stuck with this coordinate system instead, when I wrote out the linear momentum equation, I wouldn't have this term because the acceleration of that fixed coordinate system would be 0, and this would just go back to 0, and we get back our kind of simplified linear momentum equation. You can use either coordinate system, but I'm going to use the little one for this example. So let's go ahead and start writing out what some of these terms are. Body forces in the x direction will be 0. We're assuming gravity is acting vertically. Surface forces in the x direction will just be this force F that's being applied to it. The pressure all around the surroundings here is just atmospheric pressure or zero gauge pressure, so we don't have to worry about that. Even in a jet, it's atmospheric pressure because it's a free jet. The force that the floor or the ground exerts on the cart's in the vertical direction, and we're only worried about the x direction, so we don't have to worry about that. So the only thing we have to worry about is that F, and that's in the minus x direction. Okay. Now this last term, involving the acceleration, that's just the acceleration times, so here's the acceleration times the mass inside the control volume. So the acceleration of the control volume will just be how, well, it's the acceleration of the coordinate system. It's just how this coordinate system accelerates relative to that coordinate system. But this coordinate system's fixed to the cart, and the cart is accelerating at a constant acceleration a. Okay, so that will be a times rho dv integral cv. This is just the mass inside the cart. So that's the mass inside the control volume. I should say it's the mass inside the control volume, not mass inside the cart. So that's what that term looks like. Let me come to this term now. This is the time rate of change of x linear momentum in the control volume using my little x coordinate system. This term will actually be 0 for our case, and let me explain why. This is probably the hardest part of this problem to understand. Specifically, I want to focus on this u sub x. This is the velocity in the x direction of all the stuff inside my control volume. Now, if we're standing on the control volume, then the velocity of the cart looks like it's stationary, right? The x velocity of the cart when I stand on it looks like it's 0. It's not moving. Same sort of thing with most of the water inside my control volume. When I stand on the cart, this velocity of the water in the x direction looks like it's 0. The only part, there is a little bit like right in here that doesn't look like the velocity does look like it's changing with time in the horizontal direction, but it's a small amount. So we're going to neglect that. So this term is 0 because, well, it's actually approximately 0. Not everything has a constant, ux velocity or a 0 ux velocity, but most of it does. And the reason for this is because ux is approximately 0 using the coordinate system fixed to the control volume. It's not 0 because it's steady, so you have to be careful of that. This is not a steady problem. The mass inside the cart is changing with time, and the cart is also accelerating. But it's 0 because the ux looks like it's 0 as we stand on the cart. I think it's important to include this expression in parentheses here so that you fully understand why this term is 0. Often this term doesn't show up in a lot of the problems we work because it's steady, but here it's not steady. It's 0 for a different reason, so I think it's important to write down why that is. All right, let's move on to this x momentum flux term. Let's evaluate the ux term. So this is the velocity of whatever's crossing our control surface using our little xy coordinate system. So when we come up here, the velocity, the only thing that's crossing the control surface is this stream of water that's coming in, right? So it's a stream of water coming in. And using our coordinate system here, the velocity of that stream of water will be v minus u. So let me write that down. So this is v minus u in the x direction. Remember, it's the velocity of the water as it's crossing the control surface using our chosen coordinate system here. So it's velocity v relative to the ground, and here it's velocity u relative to the ground. So the velocity relative to the coordinate system will be v minus u. Okay, hopefully that makes sense. There are ways to check this. So for example, imagine if u was 0. If this was fixed on the ground, then the velocity coming in should just be v. Right? Okay, so this works out. Imagine if u was equal to v. So the cart was moving just as fast as the jet, then we wouldn't expect any water to be entering the control volume. So v minus u, if they were the same, this should be 0, and it is. So it makes sense I always like to kind of double check that just by looking at some extreme cases and make sure the numbers work out correctly. So the ux velocity here will be v minus u because we're using this coordinate system. So let's write that out. So it's v minus u in the x direction. This is this yellow highlighted term here. Now the next term is the mass flow rate term, but we've already dealt with that term. This mass flow rate term we dealt with right up here. It's the same expression. So it'll look exactly the same as what we had before. Okay, it'll be exactly the same. When you deal with the relative velocity, it doesn't matter what coordinate system you use, because the relative velocity, you're using the fluid velocity minus the control surface velocity. That difference will be the same whether I use this coordinate system or that coordinate system. It'll be exactly the same. So for example, here I used this coordinate system, but let me go ahead and work it out with that coordinate system. So in that case, UREL, I'll do it in blue since I'm using the blue coordinate system. We have the fluid velocity using that coordinate system. Well, we just argued a moment ago that it's v minus u in the I hat direction. And then we'll have the minus the control surface velocity. But the surface of the control volume here using this coordinate system is 0 because we're standing on the control surface, so it doesn't look like it has any velocity. So that's just 0. And so we'll end up with the exact same result that we had previously. So the relative velocity ultimately is just v minus u in the I hat direction. Let me highlight these so you can see that this is v minus u is the u fluid velocity, and here the green is the control surface velocity. So you can see that the result here of v minus u in the I hat direction is exactly the same as the one that we did previously using that red fixed coordinate system. So when we deal with relative velocities, it doesn't matter which coordinate system we use because we're dealing with a difference. Okay, hopefully that makes sense to you. So our mass flow rate term will look exactly the same as what we evaluated previously. So it'll be a minus rho v minus u times a. So let me put that in here. Minus rho v minus u times a. So that's our mass flow rate term. All right. So now we have everything we need in our linear momentum equation expression. So let's just go ahead and simplify it. So on the left-hand side, we'll have a minus rho v minus u squared times a. On the right-hand side, we have a minus f minus a times the mass of the control volume. And we want to solve for the force. So we can rearrange this. So this is our expression for the force. So this is the force we need to apply in order to keep this cart moving at a constant acceleration. And to be thorough, we know that u and the mass and the control volume are functions of time. So we should substitute those in. U is given right here. And then the mass and the control volume we found earlier. So we'll write those down. We'll just repeat them here. So u is just, oops, try that again. U is a times t, and the mass in the control volume is the initial mass plus rho vt minus 1/2 at squared times the area. Yes. So you could plug these in up here if you wished. All right, so that's the acceleration, or the force that we'd have to apply in order to keep the cart going at a constant acceleration. Let me work this problem one last time, but just a different way. So when I did the linear momentum equation here, I used this blue coordinate system, but let me just show you that you can also work it using the red coordinate system. You should get the same result. It shouldn't matter what coordinate system you use. So I'm just going to show it to you that you can also get it using the red coordinate system. Personally, I prefer to use the blue coordinate system that's fixed to the control volume because I think everything is easier to solve that way. It just makes more sense. But let's work it out using the red coordinate system just so you can see it. So we're going to do the linear momentum equation in the capital X direction. So we'll write out the linear momentum equation using that coordinate system. And when we use that coordinate system, we don't have the acceleration term. So up here we had this acceleration term because we were using an accelerating coordinate system. Here our coordinate system is fixed, so we don't have the acceleration term for the coordinate system. So we don't have to worry about that. Let's start with some of the easy terms. The body forces in the x direction are 0. Surface forces in the x direction still minus F. Let me evaluate this momentum flux term. This is where the x linear momentum crosses into or out of the control volume. The x velocity of stuff crossing our coordinate system. Now remember, this is with the velocity relative to our capital X coordinate system. So when I come back up to the picture, the velocity, I'm going to erase some stuff here. The velocity of the fluid as it crosses our our control surface using that coordinate system is just v. It's just that velocity that it's going. This is not a relative velocity. This is just the velocity of the fluid using our coordinate system as it crosses the control surface. So it's just v in this case. So this will be v in the positive x direction. So again, this is our ux term. Now our mass flow rate term will look exactly the same as what we had previously. It's still going to be this term. It's still the same term that we had even back up here with conservation of mass. Because the relative velocity does not matter. It doesn't depend on what coordinate system we use. So this will be a minus rho v minus u times a. So that's our mass flow rate term. So that one, again, doesn't depend on what coordinate system we use. Now, the part that I think is kind of the trickiest is this one. This is the time rate of change of x linear momentum in our control volume. So keep in mind that this term is just like a ddt of mass of the control volume times the velocity in the x direction of the control volume. I'll just write it like this. Okay, it's kind of like that term, but just integrated, right? So we have two things that are changing using our capital X coordinate system. Well, first of all, the mass in the control volume is changing with time, but also the X component of all of the stuff inside the control volume is changing with time. I should have put a capital X here. So let me expand that out. That looks like a mass times dux dt of the control volume plus ux of the control volume times dm cv dt. Okay. Again, just to recap, this expression, just the integral part, is the x linear momentum in the control volume. So that's just like the mass of the control volume times the x component of the velocity of the control volume. I'll put a CV there. And we're just going to take the time derivative of that. So all I've done here is just expand out the time derivative. Well, let's do the first term here. We have the mass in the control volume times dux dt. Well, that'll just be the mass in the control volume times the acceleration, because remember that the control volume is accelerating at a constant acceleration, just capital A. So that this dux cv is just how the velocity here is changing with respect to time relative to our coordinate system. So it's just a, little a. Okay? So that's how I got this expression. And then this next one is just the velocity of our control volume in the x direction. It's just capital U, that's just relative to our capital coordinate system, times dm cv dt. So just how our mass in the control volume is changing with time. But if I go back up here for a second, you can see this is how our mass in the control volume is changing with time. That came from conservation of mass. So I'll just multiply by this expression. Well, actually, I have to be careful. No, actually, that's correct. I'm sorry. So that's a rho v minus u times a. So let me now substitute in to our linear momentum equation. So we have our first set of terms. Here we have our x linear momentum flux term right here, this one. Notice there's a minus sign in front of it. Let me rewrite that. And then on the right-hand side, we have the minus f. Well, if you look, these two terms you can combine together. In fact, it'll look like this. Let's see, this will be a minus v minus u times a rho v minus u times the area. I think I did that correctly. Let me just double check. Yeah. So this will just be minus rho v minus u squared times a is equal to minus f. And so then let me just rearrange that. F is equal to rho v minus u squared times area minus the mass in the control volume times acceleration. So that's what we get for our force. And if you look back up here, it's the exact same expression that we derived using our blue coordinate system, the one that's accelerating. We get the same exact expression. So we found this one using our fixed coordinate system, and we get the same result as expected. The challenge with using that fixed coordinate system, the capital XY coordinate system, in my mind, the challenge with that is this term gets trickier. You have to recognize what it is and then expand it out. I think it's just a trickier way to do the problem. It'll work out correctly if you do everything, properly. I just find that it's a little trickier and a little harder to understand. Personally, I think, 9 times out of 10, you're always better off fixing your coordinate system to the control volume if your control volume is moving. It just makes things a bit easier. When you evaluate the relative velocity term, there you can use whatever coordinate system you want. It just, whatever you find easiest. You can use the blue one or the red one. You'll get the same result. Okay, so hopefully all of this makes sense. If not, there's some other examples I'll be working through, and you can see the application of the linear momentum equation for accelerating coordinate systems in other scenarios. So we'll just go ahead and end it there.